All right. So instead of path difference, we can translate that into something called phase difference. And we say when you have path difference of 0 or entire wavelengths or multiple integer of wavelengths, they have constructed interference. That corresponds to 0 phase difference, 2 pi or 4 pi. You just keep going a complete cycle. Under this phase difference, your two waves will have constructed interference. On the other hand, if you have a pi phase difference, it's like half wavelengths of path difference. So they will go opposite. Same with 3 pi, 5 pi. Those will give you destructive interference. Okay? All right, pop quiz. If I have a phase difference of 3 pi, what is the corresponding path difference? If I have two waves and the path difference is one of them, which one will translate to a phase difference of 3 pi? For a path length, an entire wavelength corresponds to an entire cycle. And for cosine, 2 pi is a cycle. So you map 2 pi to a wavelength. Then how many wavelengths should 3 pi get mapped into? Not bad, not bad. Good. So if you have half lambda, that's destructive. Destructive is opposite. When you go through a pi, you go from 1 to -1 in cosine. So this one is pi, 2 pi, and 3 pi. So 3 pi corresponds to 3 second lambda, 3/2. All right, good. And also, when we have a pi phase difference, one of the wave has moved half of the lambda, and you kind of see that the effect is flipping up and down. It goes opposite. Remember, when you have pi phase difference, it goes opposite. Okay? So why do we introduce this terminology? Because sometimes the phase difference can be caused not by path difference, but by some other things. For example, if you have a wave coming in and hit a wall, and it got reflected, there's no such thing as path difference, but you know something happens to the wave. It got flipped upside down. So you see, getting reflected by a fixed end also gives you a pi phase difference. Sometimes you get a 0 phase difference when the boundary is a free end. And sometimes you get reflected by a median with slower wave speed. And in this case, you will have a pi phase difference for the reflected wave, but the transmitted wave always have 0 phase difference. So you see this terminology is useful, and that's why we introduce them. Okay? Any question for phase? Yeah?
Can you go back one slide to see if the
Any other question? All right, we're done with the simple math and terminology. Let's do physics. So the last type of interference we need to do is called thin film interference. When you have a thin film coated over here, the wave can be reflected by the first interface, or it can penetrate the first interface and get reflected by the second interface. So when the wave hit a boundary, it will be partially reflected and partially transmitted. When you have a film, it can cause a wave to split into two, and these two waves can have interference. You see? Now, whether these two waves have constructive or destructive interference depends on the phase difference of these two waves. The reason that the blue one has a different phase is because the wave have to go an extra distance in there, and also get reflected, and then another extra distance back there. You can adjust the thickness of this film to create different phase difference in these two waves. Now, what will happen if you adjust the thickness such that the two reflected... Oh. Let me check the recording. It's still going, good. All right. So if you adjust the thickness such that the two reflected waves have pi phase difference, which is distortion interference, then you can imagine most of the reflected waves will get canceled. The reason that they do not cancel exactly is because the portion of wave that got reflected and transmitted may not be 50-50, and you can have wave that got reflected once and then back and forth. So it's not exactly that simple, but the dominant one will be the first one that got reflected, and then the first one that got transmitted and reflected. So these two is the most important component we have to consider. And the physical effect of this is that you can adjust the thickness of your film such that most of the incoming wave or light can just go in and penetrate the film. When will this be useful? Sometimes you want to minimize reflection, such as having a camera. You can coat a thin film on the lens of your camera such that it can have higher sensitivity to the light from the environment. That's what you want if you are an engineer working on creating better camera. Now, on the other hand, you can also adjust the thickness of the film such that it causes the reflected wave to have distortion interference. So before I explain the physical consequence, let's review again. What does this phase difference mean if they have distorted interference? These two have constructed interference now, and which phase difference should correspond to constructed interference? Why is there an E? Good. Indeed, so you see they have constructed interference which do correspond to 0 or 2 pi or 4 pi. Pi is destructive and half pi is like somewhere in between. You can have, in general, any value for the phase difference. But in this case, the only possibility down here is 0. So what is the physical consequence? When the two reflected waves have constructed interference, then overall you will see most of the wave got reflected or most of the light got reflected, and only very few got penetrated. So you can adjust the thickness of this film to maximize the reflection. This will be useful when you want to coat the window of your car to decrease the sunlight coming into your passenger seat. Okay? So you can use this thin film interference to create different type of reflection rate or transmitted rate. Any questions so far? All right. Now, this thin film interference is so the key of this thin film interference is the thickness of the film and the wavelength of the wave. This is the picture you will see if you put a glass that looks like this on top of the mirror and you look from above to the bottom. You will see this color pattern, and this is caused by the fact that different color of light have different wavelengths. When light goes from above to below, you can see some of them will be reflected by this interface, and then some will penetrate and then get reflected by the second interface. So in this case, the thin film is the air film between the glass and the mirror down there. Now, we don't have to analyze too much, and we know that no matter what condition we are looking for, it should happen first for shorter wavelengths, because when you are closer to the center, the thickness of the air film is shorter. So no matter if you're looking at the thickness equals a wavelength, two wavelengths, half wavelengths, you know it will match the wavelengths first by the shortest wavelength. So the light with shortest wavelength will match the condition you're looking at first, and then as you go further to the side, the thickness increase and the color with longer wavelength will match the condition you're looking for. Let's say you want to look for constructed interference, which makes the color most apparent. Then the first one that matches the condition for constructed interference will be the blue one, because it has a shorter wavelength. And then as you go out, colors with longer wavelengths will match the condition. So it goes from blue to red, and then it will repeat, because for constructed interference, you can have 0, lambda, 2 lambda of path difference, or 0 to pi, 4 pi. So this line is 0, and this line is pi, and then 2 pi, so on and so forth. But the order should be the shortest correspond to the thinnest film, and then the longest wavelength corresponded to the most widest film. Okay? So this is also the reason why the bubble will have the color, because the bubble film can have different thickness at different part, and different color have constructed interference at different part. That's your homework, by the way. So any question? Okay, so we are done with the interference. Now we are going to enter the part called geometric optics. So first we have the law of reflection. When a light comes in and then goes out, the incident ray will make an angle with this vertical line perpendicular to the surface. The law of reflection tells you that the angle comes in equals the angle come out. That's pretty simple, right? So you have to memorize it. That is the easiest formula you'll ever see in your physics class. Let's see if I can demonstrate it here. Good. So here are some laser light shining toward a mirror. I hope you can see that if I make a 90-degree in, it will come back 90 degree. And if I make a 45-degree, then the incident and refracted angle will both be 45, which add up to a 90-degree. You have a lot of mirror in your home, so I believe this is elementary for you guys. Okay? Any question on the law of reflection? Good, because now is your quiz time. If you really know how law of reflection works, tell me which one makes more sense. A light go in, go refracted, and bounce back. Which light should be the one that follows the law of physics? Incident angle equals refracted angle. Oh, should I bring a projector? Is there a way for you? So put your vision on the angle between this incident ray and the dotted line with the outgoing ray with the dotted line. I hope you can see that for A, the angle that it makes with the dotted line is wider than the incident angle. So you know A is too far. The refracted angle made by A is too big, so it's not the answer, and the answer is B. Okay? Any question with the law of reflection? Yeah?
What if the surface is not flat or it's not laid down flat?
So every curve looks flat if you zoom in enough. That's calculus. So you will look at the dotted line at that point perpendicular to the surface, which will be flat if you zoom in enough. Any other question? And also you don't need to, yeah, I will make sure the surface is flat, is smooth enough for you to use human eye to determine the normal line. Okay, so that's reflection, pretty easy. The next is called refraction. It's about what will happen when a wave enters a different medium with different speed of wave. Let's say the wave is entering glass, then the speed of light in glass is smaller than the speed of light in air or vacuum. The speed of light is the fastest in vacuum. Air is a little bit slower, but not that much different. If you enter glass or water, then the speed of light will be significantly slower. So we learned that the incident wave and the transmitted wave should have the same frequency, because if I hit the surface 3 times per second, then the wave should be generated 3 times per second. So the frequency must be the same. But we say the speed of light, the speed of wave is v equals f lambda. So if the frequency is the same, but the speed of light should be slower in the glass, it means that the wavelength of the light in the glass must be shorter. So you should see the waveform like this. When light enters the glass, its wavelength becomes shorter, so the speed slows down. Or the reasoning should be that because the speed slows down, so the wavelength becomes shorter. Okay? So when light enters glass, its speed slows down and wavelengths become shorter. That's very important, because when we look at the scenario which the light enters the glass with an angle, we know that the speed of light in the glass must be smaller, which means the wavelength of light in the glass must be shorter. Then this picture is not right. You see, in this picture, the wavelength in the glass and the wavelength in air is the same. If the wavelength in the glass is shorter, then so the wavelength should be shorter, then what must happen is that the wave must turn its direction such that this wavelength in the glass is shorter than the wavelength in the air. So when a wave enters a slower medium, when a wave enters a medium, you should see that the direction of the wave should change, like here. You see inside the plug, the light is going a little bit down instead of horizontal. So that's the reason why a wave enters. So this is why when a wave enters a different medium, the direction should change. Any question? Let's look at this again. Because the wavelength should be shorter, so the direction must change. Okay? Any question? All right. So we see that the direction will change. Instead of going this way, it gets a bit closer to the dotted line. Again, we use this dotted line perpendicular to the surface to describe how refraction works. Here, we are looking at the scenario which the wave goes from a faster medium to a slower medium. When a wave goes from faster to slower, we see that this incident angle will be bigger than the refracted angle. So this is called a refracted angle. It's the angle between the refracted light and the normal line. So remember, when you go from fast to slow, the light ray will bend toward the normal line. Okay? That's common sense. Make sure you remember that. On the other hand, when you have a light ray that comes from a glass into the air, now you are going from slow to fast. And you can see that if you go from slow to fast, okay, I hope it looks like in the glass it is horizontal and that it bends away from the normal line. So from slow to fast, you bend away from the normal line, and from fast to slow, you bend toward the normal line. Either way, the line in the slower median should be closer to the normal line. Any question? Do you know what's coming? If there's no question, show me you understand how refraction works. So here I have a light ray going into a piece of glass which the speed of wave slows down. So if the speed of light slows down, should it bend toward the normal line or bend away from the normal line? All right, pretty good. Indeed, when you go from fast to slow, you bend toward the normal line. Line B is a line which the light just goes in straight line. So compared to straight one, you have to get closer to the normal line, and like if you see. So the answer is C. Okay. Now, some terminology. Instead of saying speed of wave, we will use a thing called refractive index to describe the optical property of this material. Instead of saying the speed of wave is slower, we define something called refractive index, which is the speed of light in vacuum divided by the speed of light in that medium. So the speed of light is, let's see, 1,000 million. The speed of light is 299 million. No. Is it all right? The speed of light is 299,792,458 meters per second. The reason I put out all the numbers is because this is defined. The speed of light is defined to be this fast, and it will never change. The way we do this is by adjusting the definition of second and meter. So if you have a high precision clock, we adjust how long a meter should be based on this number. Because this number will never change, the speed of light in vacuum is always this constant. So it's more convenient to just define it to be this, so we don't need to worry about the precision. The precision of this number is as much as you want. There's 0.000, as many zeros as you want. But approximately is 3 times 10 to the power of 8 meters per second. Remember that? It's 3 times 10 to the power of 8 meters per second. But in glass, it's slower. It's just 2.25. So if you divide something bigger with something smaller, you get a number bigger than 1. So that is the refractive index of this is water. So light is slower in water. But instead of saying the speed of light is slower in water, we say the refractive index of water is 1.3. So that's how we describe the optical property of material. Okay? Now, What is the dimension of refractive index? Dimension analysis. It is the speed of light in vacuum divided by the speed of light in the material you're looking at. For water, it's 1.3. 1.3 what? What's the unit? Good, its dimension is. Just like the phase is a number. Pi, 2 pi, just a number, dimension is. Good, you don't need to specify a unit. Or you can specify its radius, but we all know we use radius. Refractive index doesn't have a unit, it's a ratio. So you just give a number, and that saves a lot of chalk, a lot of things. It's always the same no matter which unit system you use. Okay? Now, refractive index is defined as speed of light in vacuum over the speed of light in medium. So in medium, light slows down. If the denominator becomes smaller, the number becomes bigger. So it means that if you have a big refractive index, the speed of light is slower. Okay? Bigger refractive index means the material will slow down the light more. It slows the light more, so that's why the refractive index is bigger. And because the speed of light is the fastest in vacuum, the refractive index of a material must always be bigger than 1, because if the denominator is always bigger than the numerator, then it's always bigger than 1. Okay? So have some sense that a refractive index should be bigger than 1. If you do your experiment and give me, your lab TA will laugh at you if you give him a refractive index smaller than 1. Okay? All right. Any question with refractive index? Remember, big index means slow speed, because we are going to combine that with the refraction, law of refraction. Instead of giving you the speed of light, I give you the refractive index. If you go from high index to low index, does it mean speed out, speed down? And if it's speed out, speed down, should it go away from the normal line or go toward the normal line? So remember, big index means it slows down the light more. So when you go from 1.3 to 1.1, you go from slow to fast. When you go from slow to fast, you bend away from the normal line. Which means the answer is C. Good job. Okay. All right. So we learned that if you have a light coming from slow to fast, the refracted light will bend away from the normal line. But also it's just part of the light. Another part of the light will be reflected by the boundary. That's usually the case. In general, when you encounter a boundary, it will be partially reflected and partially refracted. Now, if I make the angle a little bit bigger, then the angle you make with the dotted line at the refracted side should also be bigger. And I can find the light such that it almost go parallel to the surface. And then there's also a partial reflection. Now, at this angle, the light is already bent very close to the surface. What if I incident the light with an even bigger angle? So if you learn the Snell's law already, the mathematics will tell you the light will bend back into the glass with some angle. But physically, that's not what happens. What happens is that all the light will be reflected by the interface. even though this is like water and air, they are both transparent. But if you shoot a light from water and make a big enough angle, you make a big enough incident angle with a dotted line, then when the angle is bigger than a certain value, all the light will just be reflected back because the refraction is not allowed based on some physics law. The tendency is clear because the angle just becomes bigger and bigger. At some value, all of the light must be reflected. This is called total internal reflection. Internal because you are still inside the original medium. Okay? Any questions so far? So total internal reflection has a very important application. Your high-speed internet. So people used to use some wire to transform information, but we know the fastest thing that moves in the universe is light. So if you want to transmit information in the fastest way, you have to use light. To guide light, you can create a fiber with bigger refractive index in the core and smaller refractive index at the outer coating. So when you have a light inside the core and make the angle big enough, the reflected light is not allowed and all the light will be reflected inside the core. And then you can just keep the light inside your fiber and then transform the information as far as you want. And it goes as fast as 7.5 round of Earth per second. That's how you download whatever thing you're looking at in your internet. So this is a giant one. This has higher refractive index, air has lower. So when I have laser in there, it's going from can you see the laser is reflecting inside the optical fiber? So you can bend the fiber and let the fiber guide the light, and then this is how you download things in high speed. You can go as bend as you want, and the internet just go do. This is what's happening to your internet when you're watching YouTube. 4K, all right? All right, that's total internal reflection. Any question? Remember, it's so too fast. So when you are bending away from the normal line, you have to bend too much just that it just got reflected. Next thing is called dispersion. Speed of light is a constant in vacuum. It's 399 something, about 3 times 10 to the power of 8 meters per second. And that is true for all color of light, any wavelength. But when light enters medium, different wavelengths will cause different interaction with the medium, and the speed of light can be different. So here, a white light enters a triangle prism, which is made with some glass, and the speed of light is slower in glass. When the speed of light is different in the medium, it will cause refraction. It will bend the light because the speed is different. And if you slow down, or if you got slowed down by the medium more, you should get bent more, because this bending is all caused by the slowing down of your speed. So when you see different color, the one that got bent more should be slower. So if experiment tells you that when you shoot a white light containing all the color of light going into the prism, and you see the red one doesn't get bent as much as the blue one, then which color travels the slowest in gas? put in your answer. I have to adjust my PowerPoint because I put in the wrong answer. We are still recording the site. Good. Let me change my answer real quick. Okay. So remember, the reason that the light gets bent is because the speed is different. In this case, the glass slows down the light. The light got slowed down, and the more it got slowed down, the more it got bent. Here you can see that the blue one got slowed down the most, so the slowest light in glass will be the blue light. Okay? So let's call dispersion. When the wavelength or frequency actually change the speed of light. I know earlier I said v equals f lambda, so, but frequency doesn't change the speed, yeah? What? Well, there won't be, this kind of problem won't happen in the exams, okay? So, even though I said the speed of light, the speed of wave is not affected by the frequency, but in this case, it does. When this kind of thing happens, it's called dispersion. When you have dispersion, it means that the speed of wave is actually affected by the frequency and wavelength. For string wave, there's no dispersion. For light wave in vacuum, there's no dispersion. But for light wave in medium, there will be dispersion. And those are the only two kinds of wave you have to study in this class. String wave, no dispersion. Light wave in vacuum, no dispersion. And light wave in medium, you do have dispersion. The blue one is the slowest. Okay? All right. The next thing we have to understand about light is called the polarization. So we said that the light is electromagnetic wave. Here I cut away the magnetic field because we want to focus on electric wave. Electrons carry electric charge, so that's why the electric field is more important. They carry electric charge, not magnetic charge. And what we can do is design something called polarizer. Here's a polarizer. You can see some effect by, do we have things? Does this work? All right, you can see here. Oh, okay. So what happened is that when I adjust the angle between these two polarizers, you can see the light that passes through the two polarizers is different. Here, almost no light pass through, and here it's brighter. This is caused by the fact that the wave we're looking at is a transverse wave. What I'm holding here is actually some molecule with a lot of atoms in there. We call them polymers. It's a long molecule. And we stretch the molecules such that they're aligned in the same direction. When they're all stretched, aligned in the same direction, the electron on the atom can only move along the direction. So only the electric field oscillating along the direction can pass through. Here, you have an unpolarized light, which means the polarization is random. It's in all kinds of direction. But only those that have the same polarization can pass through the first vertical polarizer. And the intensity just got decreased by half. Because energy is what conserved, so intensity is what conserved. And light have two polarization. It can be vertical or horizontal. So if you only allow vertical light to pass through, then you only allow half of the polarized light to pass through. So half of the energy gives you half the intensity. And after the first polarizer, all this randomly polarized light, so all the horizontal one got blocked, and only the vertical one pass through. And if the second polarizer is horizontally polarized, then the vertical light cannot pass through, which means you are blocking all the light after you put these two polarizers in perpendicular. Let's look at that in slow motion. A polarizer can be placed vertically or horizontally. The polarization of light can also be vertical or horizontal. When you have a vertical polarizer and your light is vertical, then it can pass through, no problem. But if you have a horizontally polarized light, the electron on this polarizer cannot move left and right. So the electric field of this light cannot pass through, therefore the light will get blocked because of the polarization. Similarly, you can have horizontally polarized polarizer. You just rotate the polarizer by 90 degrees, and then in this case, the vertical light will be blocked and the horizontal light can pass through. Okay? So far, so good. Now, what if I go diagonal? There's no way there's only vertical and horizontal. I can go diagonal, right? So what happened is that this electric field is a vector. You learn in 9A that vector have components. When your electric field is making an angle with the polarizer, you can look at just the component along the direction of polarizer, and that part of the vector can pass through the polarizer, while the perpendicular part will be blocked. So what happened is that your light will partially pass through the polarizer, and after you pass through the polarizer, it's no longer diagonal, it's vertical. When you have a diagonal light passing through a vertical polarizer, the only component that passes through is the vertical one, so the light after the polarizer becomes vertically polarized. You go from diagonal to vertical. All the light that comes out from a vertical polarizer must have vertical polarization because all the horizontal component got blocked. Okay? Any question with diagonal polarization? Yeah.
So what would happen if you change the polarizer or angle the polarizer in a diagonal way instead of the light with
Good. So only the relative angle matters. You can have vertical light. You can have vertically polarized light, but put the polarizer diagonal. It's all about this relative angle. Just tilt your head and you'll see what you want. Any other question? Okay. Yeah, so when you have diagonal, when you're making an angle, you take the component along the polarizer. So let's review. If you have an unpolarized light passing through a polarizer, it blocks all the horizontal light, leaving you with vertical polarized light. And if you put another vertically polarized polarizer, then it just pass through because they are already in the matching polarization. However, if you put the two polarizer in perpendicular position, then the light passing through the first one becomes vertically polarized, which cannot pass through the horizontal polarizer. That is what happened when I put these two polarizer. So here they are both vertical, but if I turn the second one 90 degrees, then one is vertical, one is horizontal, so the light is just completely blocked. Partially blocked, completely blocked. Okay? This is the tendency you should see. When the two polarizer is perpendicular, then it blocks all the component of the light. Okay? If you are just making an angle, then the vertically polarized light do have some component along this diagonal direction, so it will partially pass through the second polarizer, but the polarization will again be changed in this direction. So this have some application. The one application is the 3D movie. The 3D perception that we can see is caused by having two eyes. If you cover one with your eyes, then you will have hard time judging the distance of object. This is because the two of your eyes is separated by a distance, so they are actually receiving two different images. When I'm looking at a finger, I have a feeling of distance because my left eye is seeing this part of the finger and the other eye is seeing at a different part. So together, my brain processes such that I see a 3D object with a distance. So in order to have 3D effect, the movie theater have to somehow let both of your eyes see different image. Even though you have one screen, your two different eyes need to see two different images. The way to do that is to polarize the light and have you wear glasses. When you go to a 3D movie, you wear glasses. Those glasses are actually two polarizers with two different polarization. So your left eye will only see one image, and your right eye will see other image. Your eyes see two different image, and that's how you see a 3D effect. Okay, that makes a lot of money with a very cheap object, polarizer. So let's this one, okay? After the polarization, there's something called Brewster angle. So this is the combination of polarization and refraction. Let's say this is the water surface, and I have my light polarized like this. So on the screen, you are looking at the electric field going in and out of the screen. That's why I drew this dot and cross. All right, dot is coming at you because when you see an arrow coming at you, you see a dot. When you shoot an arrow, you see the cross from the feather. So it is in, out of the screen, which is what I'm doing here. The light is polarized like this, so it's going in and out of the screen. Now, when I shoot this light ray onto the surface, and the polarization is perpendicular to the incident plane. The incident plane is the plane created by this normal line and the incident ray, refracted ray, transmitted ray. There's a lot of straight lines, so you can define a plane. Here, the incident plane is this one, not this one. This is not the incident plane. Here is my incident plane. And you can see the electric field is perpendicular to the incident plane. Now, you see when the polarization is perpendicular to the incident plane, changing the incident angle doesn't. So if I am shooting the light ray into the water surface like this, the electric field is rubbing the water surface horizontally. If I change the angle, it's still rubbing the surface horizontally. No matter what angle I'm incidenting my light ray, the electric field is always rubbing the water surface horizontally. So you know nothing interesting will happen because the way that the electric field rubs the surface is always the same. But this will be different if you look at another polarization. So when the polarization is not perpendicular but parallel to the incident plane, changing this incident angle will change how the electric field penetrates the water surface. A smaller incident angle, this is smaller because this is the normal line with the light ray. Smaller incident angle makes the electric field kind of parallel to the surface. But if I have a bigger incident angle, now the electric field is going right into the surface, penetrating it. So you see, for this polarization, changing the incident angle should change how the electric field or how the light ray interact with this water surface. So something interesting might happen. So far, so good. This is harassing the water surface in different way, penetrating and just rubbing compared to always just rubbing. Okay? Okay? So what will happen if you have this polarization parallel to the incident plane? What will happen is that there exists a special angle called Brewster's angle, such that when the light goes in, all of them will go into the water. None of them will get reflected. This is like the opposite of total internal reflection. Total internal reflection is that all the light ray will get reflected. Here, if you have the right polarization and right angle, all the light will get transmitted into the water without making any reflection. So this specific angle is called the Brewster angle, and it is, of course, related to the refractive index of these two objects. Here, I think N2 is the water one. In your homework, this is just plug-in number. I will not derive this formula in this class because you need electromagnetism, and the derivation in your textbook is wrong, so just don't worry about it. So you see, if somehow you are very far away from the, let's say you are on a helicopter, and there's the ice of the North Pole or South Pole that you want to measure its refractive index for whatever reason. Then, because you don't have access to the thing under the glass, you cannot measure the refractive angle. What you can do is to shoot the light with the correct polarization. Remember, it has to be parallel to the incident plane such that it can penetrate the surface at some angle. Then you can have another helicopter try to measure the reflected light. When you see there's no reflected light, it means you are shining the light at Brewster's angle, and you can use the formula to deduce the refractive index of the ice without knowing the refracted angle. Okay? Any question with Brewster's angle? Yeah.
When you have a horizontal angle, will the light penetrate the surface and be reflected at the same time?
Yes. So any other angle will have partially reflection. This only happens at a specific angle. If you go away from this angle, some of the light will be reflected. Any other question? Yeah.
N2 and N1 the refractive of
air. Refractive index of air and water.
Okay.
I think N2 is the water one. You can check the textbook or check the homework. On homework, it's well indicated. But anyway, it's related to the refractive index, yes.
Is this only for water?
Anything. Anything with refractive index will have a Brewster angle only for this polarization. If you use the light with polarization perpendicular to the incident surface, then there will always be partial reflection. There's no such thing as Brewster angle for this polarization. You must prepare your light with the polarizer, put the polarizer in the front so the unpolarized light got polarized into this polarization, and then adjust the angle and measure the reflected light. When you see no reflected light, it means you're at Brewster angle, and that gives you the refractive index. Okay, yeah?
Can you explain why the Brewster's angle is the only angle where there's no reflection?
Well, no. I know how to calculate it from Maxwell equation, but I don't think you want me to do that. Well, you know, in general, there's going to be partial reflection. So this kind of special thing cannot be too general. It's special. It happens at a special angle. Okay? Another question? So yeah.
Will there be a Brewster's angle when the field is horizontal to the water surface, or it's only like that?
So this polarization will not have Brewster angle because for this polarization, the incident angle will not affect the way that the electric field interact with the surface. It's always rubbing the surface horizontally. But for this one, you can go from penetrating the surface to rubbing the surface. And a specific angle of penetrating the surface makes all the light penetrate the surface and have no reflection. Any other question? Okay, so again, this have some important application if you're into photography. Now, I have two pictures of water surface. One is taken with a polarizer, one is not. I do not tell you which one because I want you to make a guess. So remember, if you have sunlight that enters, when you have sunlight, some of them will be reflected by the water surface. But at Brewster's angle, all the polarization that goes like this will enter the water, which means only the polarization perpendicular to the incident surface will be reflected. In other words, at the Brewster angle, the reflected light itself is polarized, and you can block that light with a polarizer. So which picture looks like you are blocking the reflected light? Good? Indeed. So if you're into photography, you don't really need to bring a polarizer. There will be polarizer designed for a lens, so you can just clip it onto your lens, and you don't have to carry a flash thing. But so the light from the sun will get reflected by the water surface and mess up your picture. But those reflected light will be purely polarized into this polarization, perpendicular to the incident plane. So you can block it with a polarizer in front of your camera, and then you can see a nicer image of the thing under the water. Okay? Last Brewster angle. Any question? All right. Next, we have geometric optics, image. So you might have heard that when you have a hunter hunting fish in the water, the location of the fish is not exactly the location of fish. So when you try to hit it with the spear, you need to adjust your angle. The reason is that the way we process image is by looking at where the light comes from. If it seems like the light comes from here, then we will think the image is there. But there's a lot of way to alter that light path. In slow motion, if you see the light coming from this point, looks like it's coming from this point, then your eyeball, which receives light from two different directions, will trace back to that point and say, okay, this is the point that the light comes from. And there's a lot of way to make light change its direction, such as a mirror. So if you have a mirror, the light coming from this point will be reflected based on the law of reflection. So your eyeball will think that light comes from this direction. It doesn't know there's a mirror. It cannot touch the mirror. And it thinks like your eyeball will think the light comes from somewhere along this dotted line, even though the object is actually here and the light actually comes from here. And when you move to the other position, the light ray just bounce back the mirror and create another dotted line, which makes you think that the light comes from somewhere along this dotted line. So if you combine the information, the light comes from somewhere on this dotted line, and that point is also on this dotted line. So two lines make an intersection, which uniquely determine where the light comes from, which is not exactly where the light comes from. The light comes from here, but your eyeball will think that the light comes from here. So when you are looking at the mirror, you know your body is not right there. You are not in the mirror, but it looks like you are in the mirror because that's where the light appears to come from. It will be more obvious or more interesting when you look at plane refractor. A plane refractor is just a piece of glass. There's no curvature. It's not a glasses. It's not a magnification glasses. It's not a microscope. It's just a plain, flat layer of medium. But here, you can see I'm just filling water into the bucket. There's a scissor under the bucket. I'm just filling water. I'm not moving the scissor. The scissor is not moving. But it appears that the scissor is getting closer and closer to you. This is because the water you fill in will change the path of the light such that your eyeball traces back to different locations. Let's look at another example. So this bucket has no water right now, and the nail is down here. And later, in some weeks, you will use this parallax to determine the location of image. When you look straight from the top, you cannot tell which one is closer, but the way you can tell which one is closer is, or the way you can tell the distance is different is by looking a little bit away, and you can see the nails no longer in line. So now, if you fill the water will change the path of the light and change where your eyeball thinks the image or the light is coming from. So physically, the nail is still down here, but because the light no longer goes into a straight line, it got reflected and then enters your eyeball. So your eyeball will trace back to some point which you think the image is, or that's where you find the image. So here, if the image of the nail and the nail on the side is not exactly aligned, you will see a difference called parallax. And when the image is exactly at the same distance as the other nail, they will always be aligned no matter which angle you view the thing. You will use this technique in one of your lab, okay? So here you see, just by having a plane refractor, you can make something appears to be closer than you, appear to be closer to you. And that's what we're trying to understand in this part of the course. All right, so plane refractor. A plane refractor usually has refractive index bigger than 1 is slower. So when light goes from slower to faster, it bends away from the normal line. Your eyeball doesn't know the light was bended. It will think that the light comes from somewhere along this dotted blue line. When you look at the light from another angle, you think the light comes from somewhere along this dotted blue line. And then combining the information, you will think that the light coming from this point actually comes from this point, which is closer to you. So this is why when you have a plane refractor, it will appear to have the image closer than where the object is physically located. Any question? Make sure you know how to draw this diagram. It's in your homework. I won't question you the location in terms of how many centimeters, but you need to know how to determine the location by drawing the lines. You need to know it should be closer, not farther. All right. In the end, we have more terminology they define. It's just terminology, not a definition. Some optical device will create an image. This one is the image. This one is the object. And sometimes the object and image will not have the same size. You don't need to know why for now, but so later in the course you will see a concave lens will create can create an image shorter than the object. In this case, we define the lateral magnification as the height of the image divided by the height of the object. So in this case, 1 divided by 4, 0.25. Okay? Just definition. You don't need to know how to find the size of the image yet. Okay? So for lateral magnification, we want to include a little bit more information. Sometimes the image will be inverted compared to the orientation of the object. In this case, we still divide the height of the image by the height of the object, but with a minus sign indicating that they are inverted. Okay? That's the definition. If they are inverted, you make the lateral magnification negative. It's not like you plug in formula. It's just, I think they do have formula, but anyway, when you see the image is inverted, then you better give me a negative magnification. If you see a negative magnification, it means that the object and image are oriented in the opposite direction. Okay? That's lateral magnification. Any question? Next, we have longitudinal magnification. We saw that the object inside water will appear to be closer. What you don't know is that it will actually appear to be shorter. But this direction is lateral, is longitudinal, not lateral. Lateral is perpendicular to the line of sight. Here is along the line of sight, just shorter. Then again, you divide the length and you get a magnification. In your textbook, it says the absolute value. So I guess you want to dodge the question of whether you want to include the negative or not. But I guess you will only be questioned about the absolute value of longitudinal magnification. Then in this case, you just always get a positive number and you divide the longitudinal length of the image with the longitudinal length of the object. Okay? So that's longitudinal magnification. Just definition. Any question? Last thing. One last thing. Angular magnification. So when you look at the object, the top and bottom will make a light ray with angle theta, and the image might make an angle different than the angle made by the object. So you divide the angle, that's angular magnification. And for angular case, it's clearly stated in your textbook that you don't care about the orientation. If the image is upside down, you still take just the angle, and the angular magnification is always positive by definition. Yes?
Does it have to be in radians?
By what?
Does it have to be in radians to calculate it?
Good. So you see this is a ratio. The ratio does not depend on unit. If you have 360 divided by 180, that's 2. If you have 2 pi divided by pi, that's still 2. So you see, it doesn't depend on the unit. Okay? Any other question? Good. That's it for today's lecture. I'll see you next week. Homework due Tuesday.